Okay, let's do a second example now. These are numbers that I pulled from the General Society survey that I used for some of my examples for the chi-square test. This particular question asked, how many years have you been with your current employer? How many years have you been with your current employer? So some people answered 0 because they didn't have a job. There were presumably a lot of pretty big numbers for the people who had been with their employer a long time, but this is not a symmetric bell curve. You know, there's like the bell would be like heavily centered in the low numbers just because when people change jobs, they sort of reset this number, and it's sort of less and less likely that that people last longer. So, you know, when people change jobs around, you know, they're going to sort of like repeatedly put themselves in the low number answers for this. So it's not a symmetric bell curve. It's got a long tail off to the right, and the people are sort of mostly piled in the lower numbers. So I don't have the raw data from the General Society survey for this. What I do have is the summarized data. So the mean was equal to 8.97. Okay, so that's the sample mean, right? That's the mean in their survey. So that's the X with the bar. Okay, where's my X bar? There we go. The sample size, we're using the letter N to indicate that, that was 875. So there were 875 people who answered this question, and the sample standard deviation was also given to us. And we need to know that if we don't have the raw data, because it factors into our formulas. So that was 8.84. Okay, so you can see that there's a high standard deviation. What I mean by high is it's almost as big as the mean. So somehow the standard deviation is like, if you take a random person, how far away from the mean could you expect that they might be? This is saying that it would be totally not unusual for someone to just answer 0, and you can't go negative, so 0 is the smallest you can go. So 0 is a fairly typical answer. I guess it's also typical to have answers like 16 or higher, but there isn't necessarily a lot of answers right around 8. They're spread out quite a bit relative to like the typical middle answer, which would be just under 9. So this is enough information for us to run the test in Minitab. So let's do a 95% confidence interval and a 99% confidence interval. We have a pretty big sample here. It's almost 1,000. So we should be able to crank our accuracy up to 99 and not have the interval be too wide. You know, this 8.97 should be a pretty accurate guess because our sample is so big. Okay, so I'll flip over to Minitab. Stat, basic statistics, one sample T. Remember, we're using T now, not Z, and we're using one sample. We're not using one proportion anymore. So one sample T. I'm just going to double check them in Minitab. Yep. Okay, this time I don't have the data in the column. I have the summarized data. Sample size. N, that's the number N. We had N equals 875 in our sample. The sample mean, we were told, was 8.97. Sample standard deviation was 8.84. Double check my options. Confidence level 95. We're going to leave this as not equals, otherwise it's going to do a weird one-sided confidence interval. And this time the graph button is grayed out because Minitab can only make the graph if it has all the data. Right now, it just has these few summary statistics. That's not enough to see how the data is spread out. So you can only make the graph if you have the raw data. And that's it. We're ready to go. So we hit OK, see what we get. So there's the three numbers we were told. They found the standard error for us. And here's our confidence interval, 8.383 to 9.557. So 95% confidence interval is 8.383 up to 9.557. All right, so what about the 99% confidence interval? We'll just redo that. Going into options, changing our confidence level to 99. Hit OK. OK. And so our answer changed here to 9199 or 8.199. So 8.199 to 9.741. 741. Okay. So it did go down to 838, and now it goes to 8199. We had to make the interval a little wider to make sure there was only a 1% chance that we didn't capture the right answer. But it's not that much wider, right? Here we are saying that it's kind of close to 9. Here we're still saying it's kind of close to 9. We just had to widen like the range slightly. But this gives us a good idea of like, if we really want to know the answer to this question, we're pretty darn confident that the answer is somewhere in the 8s or 9s. And the reason is that our sample is huge. You know, my first example where we only had 10 is a tiny, tiny sample. And the only reason I did 10 was because I was physically typing the numbers in, and it's cumbersome to type in many more than 10 numbers. So ideally, we would have hundreds or thousands of numbers, and then we could be quite confident that our guess was accurate. Of course, in the real world, there actually are cases where your sample size is small, like 10 or something. If it's like some kind of medical trial, it might be really hard to test it out because maybe you're testing on like a very rare condition and you only have like a dozen people that are able to try things out. So sometimes your sample size is small, and then your guesses, you just can't trust them very much because you haven't collected enough data. But ideally, especially in an engineering setting, ideally you'd be able to have a big sample and then be quite confident in your answers. Okay, so that's it for this example. We'll have one more example and call it a day.